Hi, my name is Matthias, and in the following video I'm going to present you DB4ML, an in-memory database kernel with machine learning support. It is a joint work between TU Darmstadt, the MIT, and the University of Sydney, and the work was led by Professor Binnig. According to a survey from Kaggle.com, 80% of all ML data is stored in relational databases. However, today ML support in DBMS is very limited. Thus, typically data is first exported out of the database and a tool like scikit-learn is run to train an ML model. Having to do the training step outside the database comes with major drawbacks. First, the export step is costly because it takes time and needs to be repeated every time the data changes. Even more importantly, data export is often not allowed from the database because of security and regulatory reasons. Therefore, an ongoing effort is to bring ML into databases. Existing approaches for ML such as Matlib in a database typically add iterative support to the SQL engine. Normally, those iterative queries are executed in a bulk synchronous manner, which means that a new iteration can start only if the previous iteration finishes. We compared Matlib, which uses this approach, with a specialized graph engine that runs the ML training outside the database named Galois, and as you can see, Matlib is magnitude slower. This is mainly due to the fact that the external ML application often use asynchronous execution schemes compared to bulk synchronous parallelism enforced by the query execution. As a result, existing approaches inside a database are orders of magnitude slower than modern parallel ML algorithms. In order to understand what are alternative models of integrating ML algorithms, let's have a look at the stereotypical execution of ML algorithms and how they are executed outside the database. On an abstract level, what ML algorithms are doing is to learn a parameter vector which represents the model for a given training set. The internal process is basically always the same. First, the parameters in the training data is read, then some calculations are done with the parameters and training data, and then updates to the parameter vector are applied. So now, to parallelize, we can split the training data and spawn many more threads, which are again doing these three steps. Read parameters and training data, calculate updates, write to a parameter vector. But how do the threads organize concurrent access to the data? We can distinguish between three major synchronization schemes. In the synchronous scheme, threads are only allowed to process at the same speed. They have to synchronize each other before every write. This is very similar to the way queries are executed in a bulk synchronous style, as mentioned earlier. But modern ML algorithms behave more asynchronously in the execution. When we now remove the restriction and let threads possibly override each other, we get a fully asynchronous execution scheme. Recent work like Hogwild for stochastic gradient descent has shown that convergence is still reached, but with much greater performance and scalability while having similar accuracy. Sometimes the asynchronous scheme is too weak and doesn't lead to convergence. Therefore, a combination of both approaches exists to combine advantages of both. By only allowing threads to progress differently within a staleness level, we guarantee more consistent data than the asynchronous scheme, but don't give away performance by the need of strong and costly synchronization. If you look at the modern execution strategies in a bit more abstract manner, this fine-grained parallel execution model is very similar to what transaction in databases provide today. How would the ML algorithm map to the transactional world? The parameter could be seen as a table that is read and updated by every transaction. Transactions would be the parallel workers that execute the training on different partitions of your dataset, and different write ordering strategies, as asynchronous or bounded staleness, could be implemented by different isolation guarantees. What is still missing is the iterative support to execute transactions several times in a row. For that, we introduce in DB4ML transactions with iterative support, so-called iterative transactions, to the database kernel and expand the isolation level guarantees to support ML algorithms. What performance benefit this model achieves, you can see on the right hand side. This gives a glimpse to the experimental results where we compared DB4ML with Galois and Madlib. More on that later. Let's dive into the high-level architecture of DB4ML. The execution of an ML algorithm is hidden from the user behind a so-called Uber transaction. This Uber transaction then instantiates multiple iterative transactions which can be, for example, responsible for different parts of the data. These iterative transactions continue to do the same steps as our ML algorithm does. First, read data, then calculate with the data, and then write results back. This is all done in parallel, and data access to the storage by the iterative transactions is coordinated by the newly proposed isolation levels. So DB4ML extends only the storage and execution engine of the database and leaves the rest untouched. Iterative transactions can be executed multiple times while preserving the internal state. One execution represents one iteration of our ML algorithm. These iterative transactions access special iterative records, and all parallelization as well as optimized data access is automatically handled by the database. Each iterative transaction is instantiated by a Uber transaction. The begin function is used to set the internal state, which can be, for example, a data range on which the transaction should operate. Then the database transaction executor calls repeatedly the execute and validate functions of the transaction in which the read, calculate and write steps of the ML algorithms are done. The iterative transaction can decide whether it wants to be rescheduled or not, which he signals to the executor. At the end, if all iterative transactions finish, the Uber transaction finishes too. Our three steps from the ML side can be simply mapped to the transaction interface as shown here. Writes are done in the validate and can either succeed or fail. So, with this we add iterative support needed for fine-grained execution of ML algorithms by extending the existing transactional model. As a base, we use the MVCC model proposed by Larsen et al. Our iterative records extend their MVCC snapshots in a version field and a fixed-size tuple array. Iterative transactions install new values into the snapshot by adding a tuple to the array and increasing the version counter. Access by the iterative transactions is very efficient because all tuple versions are present in the array. Its size needs to be large enough to satisfy the used isolation level, for example the staleness value. These iterative snapshots are scoped under one Uber transaction so that multiple iterative transactions can access the same snapshot. After all iterative transactions finish, the modified snapshots are committed by the Uber transaction to the table and become visible to other transactions. We conducted an extensive evaluation of DB4ML with two use cases. First PageRank and second stochastic gradient descent. For time reasons, we will concentrate on two significant results. This experiment compares the scalability of the PageRank algorithm between DB4ML in red and Galois in blue by plotting the runtime on the y-axis and the number of cores on the x-axis. We used 3 datasets with different characteristics on an 8-socket machine. G+ is a very dense graph which leads to a saturated interconnect between the sockets for both DB4ML and Galois for high core counts. For DB4ML it is earlier visible because of the tuple overhead. We scale in general as good as the specialized engine, which can also be seen for the patterns dataset. For PLD, which is a large and sparse dataset, our caching benefits are destroyed, which is visible by the overlapping lines. All in all, this experiment shows us that DB4ML's performance is on the same level or in some cases even better than a specialized ML engine. This experiment shows the impact of stragglers. To make this impact visible, we ran the same workload using different isolation levels, x-axis, and then plotted the runtime and later accuracy on the y-axis. We can see that the stragglers have a higher influence with a stronger isolation level in the increased runtime because workers need to wait for them for synchronization. Asynchronous execution is least affected because it doesn't have costly synchronization. But this does not come without disadvantages. In this plot, we swapped runtime with accuracy and we can see the opposite effect. Due to the weaker constraints, Straggler's stronger impact on the asynchronous accuracy, as you can see in the bottom right corner. So in general, we found out that the bounded staleness gives us a robust trade-off between runtime and accuracy. To summarize, we proposed DB4ML, a transactional database kernel with machine learning support. DB4ML consists of two major contributions. First, a new programming model for ML algorithms using transactional semantics, and second, isolation schemes from the ML context to allow efficient execution of machine learning inside the database. To support our findings, we did an extensive evaluation using a PageRank and SGD implementation, with the result that we achieve performance and accuracy competitive to specialized engines when doing ML inside the database. Due to the high-level programming model of transaction, all implementations of ML algorithms inherit all optimizations from the underlying database, and the user doesn't have to worry about low-level hardware-dependent optimization. Our runtime and programming model using transactions can be used for various ML algorithms which use iterative concepts and is not limited to the two presented use cases. So DB4ML integrates machine learning into databases as fast as specialized engines. Thank you for your attention. I am now open for questions.